molecules come together and react, bonds are broken in the reactants and new bonds are formed in the products. Since there is energy between these two atoms in a bond, these two are held together by a particular force. If you want to break that interaction, you need to supply some amount of energy. In this case, I'm going to supply 58 kilojoules per mole. So 1 mole of this guy requires 58 kilojoules of energy to be broken. That's how much energy is stored in those bonds. In order to make the same bond, what will happen is when these two come together and make that bond, what will happen is that the same 58 kilojoules per mole will be released. Bond formation always releases energy. Bond breaking always needs some amount of energy, input of energy. When energy is absorbed, the reaction is called endothermic reaction. When the energy is released, that reaction is called exothermic. Exothermic is when you have release of energy. Endothermic is when you have uptake of energy or absorption of energy. In terms of physical effects, you might have noticed in lab that for the exothermic, where there's a release of energy, you feel hot. For endothermic reactions where there's an absorption of energy, since the energy is coming from you, you feel cold. There's another way to distinguish between exothermic and endothermic reactions, and that is using what is known as delta H. And this is very important from an exam point of view. Exothermic reactions, the delta H is negative. Endothermic reactions, the delta H is positive. So a reaction will be provided to you, you'll be given delta H, and you will be asked if it's exothermic or endothermic. If the delta H is negative, then it's exothermic. It means that there has been a release of energy, most likely because of bond formation. Endothermic reactions are those that require energy, they absorb energy, and that is most likely because of bond breaking. Delta H is generally described as the energy absorbed or released during the reaction. Delta H is heat of reaction or enthalpy change. Like I said, it has signs of plus or minus, positive or negative. If the energy is absorbed, it's endothermic, delta H is positive. When the energy is released, the reaction is said to be exothermic, or the delta H is negative. The bond association energy is the delta H for breaking a covalent bond by equally dividing the electrons between the atoms. So essentially what you're doing is taking those electrons that are shared, 2 for a covalent bond, and then giving them to each of those atoms. So for example here, there are 2 electrons here in the bond, and when you break it, 1 electron goes to the first hydrogen, the other electron goes to the other hydrogen. And because we're talking bond breaking, you will need to supply energy to do this process, and therefore this is endothermic, therefore the delta H is greater than 0 or positive. The exact numbers you can figure out experimentally. In this case, the delta H is 104 kilocalories per mole. Please note the units. Bond formation, like I said, is always going to have negative values. So 2 electrons are coming together to form a bond. Anytime you see a line that is actually 2 electrons. And so because of bond formation, you're going to have exothermic. Guess the number. The number is going to be exactly the same, the value, 104, but in this case, it's going to be negative. The stronger the bond, the more energy you're going to require to break it. And that makes sense. If you're holding two things together really tightly, you're going to require a lot of energy to remove them from each other. In general, when you consider the periodic table, and so the periodic table looks something like this. And when you go down the group, what is going to happen is the bond dissociation energies are going to decrease. So in an example, you can take HF, which is F is the first element in group 7A. The bond dissociation energy is 136, or very, very high, and it's kilocalories per mole. Go down and you look at HCl. Cl is the next in the line. It's 103. Go down even further to HI, and you notice that the bond dissociation energy is only 71. So if you're comparing bonds formed by atoms in the same group of the periodic table, bond dissociation energies generally decrease down the column. So another example, a problem or an example here is one of the example problems in the textbook was you were given two compounds. One looks like this. And the other looks like this. And they're asking you which would have a higher bond dissociation energy and which would be a stronger bond. So we know that fluorine has a CF being the first in the group, and then CCl is further down in the group. Look at the periodic table, F is first, then Cl. And so CF is going to have a higher bond dissociation energy, whereas this is going to be lower bond dissociation. Therefore, this is going to be the stronger bond, and this is going to be the weaker bond. And indeed, if we look at numbers, this guy is 84 kilocalories per mole, whereas this guy is 109 kilocalories per mole. So from an exam point of view, you will need to understand that down the group, what is happening to my bond dissociation energies? They are decreasing. As my bond dissociation energies decrease, my bond becomes weaker. As my bond dissociation energies increase, my bond becomes stronger. Delta H does indicate the relative strength of bonds broken and formed in the reaction. I did say that when delta H is negative, it's an exothermic reaction, energy is released, whereas in which delta H is positive, endothermic reaction, heat will be taken in. So just to sort of summarize, endothermic reactions, heat is absorbed. Exothermic reactions, heat is released. Delta H is positive for endothermic reactions, negative for exothermic reactions. Bonds are broken in the reactants or stronger than the bonds formed in the products in case of endothermic reactions, so more strong reactant bonds than in the product. And so you're losing some of that strength, and that's something that to be considered. Here, the products in exothermic, the bonds are much, much stronger, whereas the bonds broken in the reactants are much weaker. The products are higher energy than the reactants in the case of endothermic, and in exothermic, you basically have the products which have lower energy than the reactants. Here is another type of problem that you will need to know how to do. So in this particular problem, you will be given an equation. You will be given a delta H. The equation will be balanced. And the question is essentially, how many kilocalories of energy are burned, the combustion of propane, C3H8 with O2, according to the given balanced equation, which is right here, releases 531 kilocalories per mole. So you can look at the signage here. Can you tell me what type of reaction this would be? Exothermic, because it's negative. Now, they're asking you when 0.75 moles is burned, how much energy is released? You know that per mole, you get negative 531 kilocalories. That's coming from this guy, and I'm sort of using it like, what do I want? I want kilocalories. What do I not want? Moles. So I use that 531. Mole gets canceled, and I can do the math on this guy, and I get an answer of 398 kilocalories of energy if you did this right, and you'll get a negative sign which indicates how much is released. We could go ahead and make these a little bit more complicated, and instead of giving you moles, I could give you grams, in which case you would need to convert the grams to moles and then use the delta H to convert the moles to kilocalories. So grams to moles, you'd use molar mass like I've shown you in chapter 5, and then moles to kilocalories, you're using delta H.